talk about correlation versus causation. So what's the difference, and then how do we identify when we have which one? So correlation is a statistical way to measure the relationship between two sets of data. So everything has some sort of correlation. It's just a way of comparing. So some things can be very much correlated, some things maybe not so much, but basically you're just taking two sets of data, looking at their relationship, and then we are able to calculate a number based on that relationship. Now, causation is a little bit more different and it's a little bit rarer. Causation is very close to the meaning of a cause. It means that one thing causes the other. So we can always have some sort of correlation. We don't always have causation. So I'm going to add this in. This is much rarer than correlation because you have to be able to prove that one thing causes another thing. So for example, we'll look through a couple. You can have correlation without there being causation. So there is a correlation or relationship. So that's one of the keywords you kind of want to relate is relationship. There is a relationship between the number of firemen fighting a fire and the size of the fire. Now that kind of makes sense. If there's a fire, there will be firefighters. But does the number of firemen cause the size of the fire to grow? So yes, there is a relationship. However, this does not mean bringing more firemen will increase the size of the fire. So again, there's a relationship. If there was a large fire, yes, there's going to be a large amount of firemen. But if you were to bring more firemen, that doesn't mean it's going to increase the size of the fire. So the fireman is not the cause of the fire. There is just a relationship between them. So another example. A recent study showed that college students were more likely to vote than their peers that were not in school. So is this a correlation or just a causation? Okay. So for this one, can we prove that because the students are in college, that is the reason that they're more likely to vote? So yes, there might be a relationship, a correlation, but is college the cause they're more likely to vote than the kids not in school? The answer would be no. So we can only say that there is a correlation. We cannot prove specifically that college is the cause that they're more likely to vote. Okay. So number 2, Dr. Shaw noticed that there was more trash in the hallways after second period than first period. So we're thinking, is there a relationship or is there a cause? So yes, there's a relationship that there's going to be more trash in second period than first period. But is second period the cause of the trash? So that would be the causation. What is causing it? Second period? No, that would not be the cause of the trash. There's just a relationship that later in the day, there might be more trash. So again, this one is going to be correlation. So last one, you hit your sister and she cries. Is there going to be a correlation between getting hurt or hitting somebody and crying? Yes. Is hitting the cause of the crying? Can we say that this would be the direct cause of crying? Yes, because it happens right after. She cries directly after being hit, and we can pinpoint the hit as the cause. So this is an example of causation. So one thing we have to remember, everything has correlation. Causation has to be very obvious and proven, which means it's much more rare. So basically, if you're second guessing, it's probably not a causation. So what we're going to focus now on is correlation. Correlation can be measured by a correlation coefficient called R. So we're actually going to be able to calculate the correlation between two sets of data. So correlation coefficient, and we call that R. Now, R is a number between -1 and +1. And there are 4 traits that we can look at with correlation. We can look at the form of a correlation of data. We can look at the direction it's going in, think up or down, positive, negative. We can look at the strength of the data, which is R. And then we can see if there's any outliers. Okay, so we're going to look at them one at a time. So don't get too overwhelmed with the traits. We're going to focus on each one and explain what it means. So form. That's just literally describing the shape of the data. So if I look at this scatter plot, the data, what is its overall shape? It looks like it's the shape of a line. So we would call this a linear form. Is it perfectly linear? No, but it's linear in form. Here, this is a curve like this. Now, we haven't gotten into these yet, but this is called a quadratic shape. So even though it's not a perfect quadratic, like one continuous line quadratic, it's taking the form of a quadratic, so that's what we would call it, quadratic, as a U shape. Here, it's not perfect, but this curve where we go up, dip, and back up, this is called cubic in form. So again, not perfect, but that's the shape. Here, we can't really see any form taken. It looks like our data is just all over the place. So we would say no form or none. There is no shape, there's no form. And then here, this one should look familiar since we just finished this unit. Here we are taking a sharp drop and bottoming out. This is an exponential shape. So these two we've worked with linear and exponential, no form, and then this would be a quadratic form and a cubic form. So again, just seeing what the general shape is taking. So that's form, that's it. Next is direction, and this is very, very simple. Is it positive or is it negative? So direction is kind of taking the overall shape, and is it generally going up over time or is it generally going down over time? So these are 2 linear examples. So linear, this looks like it is a positive direction. Here, the linear graph looks like it's going in a negative direction. And that's it. Like, is it going up over time or is it going down over time? Is it positive or negative? So right now we have form, which is the shape. So this one would be positive. This would be negative because on both ends it's going down. Positive over time, no form, negative over time. Now we're looking at outliers. This is just being able to identify if we see one. So here we have a linear shape. This looks like it doesn't belong, so we would say we have an outlier. Quadratic in shape, this looks like it doesn't belong. It should be up here closer to the data, so that would be an outlier as well. So just being able to see generally if something doesn't belong. Now, this is going to be the most complicated out of it is the strength. Strength is basically how closely or how tight your data is together. Okay, so obviously you can see this would be considered weak data on this end. And as we move to the right in these picture examples, it gets tighter and tighter to almost a complete linear type shape. And we would call this strong data. Now, strength is our correlation coefficient, and we can actually attach a number to it. And we're going to learn how to calculate it a little bit later. But right now, we're just going to kind of estimate the strength. Strength can range from 0 to 1. Where 1 is a perfectly inline shape, 0 means absolutely none, like we cannot see it at all, like completely scattered. We would say 5 is a medium strength, and then, so I would say like maybe medium here, this is perfect. If I had something that was weaker, I would maybe call it like a 0.3. And then like a 0.8, that would be strong, but not perfect. Okay, and then like, so for example here, I might call this one a 0.3 in strength. It's pretty weak, but we can still see a shape. 0 is when there's no shape. So we still have a shape, but it's very weak, very scattered. This is moderate, like it's a very tight cluster, but it's still kind of, you know, a little bit of width across. So this might be a 0.5. This is pretty strong. It's not perfect, but we're very close to a straight line. And this one isn't quite perfect, but we would just say it's a 1, if not like a 0.99. Like this is very close to perfect, so we would just kind of say it's a 1. So 0 to 1 on the scales. So one thing we have to remember though is that R can be negative. So these are all positive because we're going in a positive direction. If we were to go in the negative direction, we would just put a negative in front of all of these numbers. So negative just means the direction. The value is how strong it is. So when we're looking at being able to rank correlation coefficients in order from weakest to strongest, we're not looking at the negative signs. We're looking at how close it is to 0 in general. So for example here, if I look at all of this data, this one right here is the closest to 0. So that is going to be my absolute weakest. Not negative 0.98, not negative 0.81. Even though those are negative, their strength is very, very strong. It's just strong in the negative direction. So 0.07 would be the weakest. 0.43 would be next. Then the negative 0.81, and then the 0.87, and then the strongest is actually the negative 0.98. It's very, very strong. It's going to look like this. It's just going to be going down. That's the only difference, is it would be going down. Okay. So go ahead and try and rank this one on your own, and that's where we're going to stop for today. So this is our last one. Just go ahead and try and rank this least to greatest or weakest to strongest. I'll give you the answers in just a second. Try it on your own, and then we will be done. Okay, so weakest, we're looking for closest to 0, so that would be our 0.04. Next, we have 0.32. Then we have negative 0.42, a 0.63, and a negative 0.65. So weakest to strongest, weakest absolute value. These are stronger, just in the negative direction. So that is it for today. The rest we will do in class.